Okay, why don't we get started? So we're really happy to have Susanne and Yelin who will tell us about quantum chemistry on a quantum computer.
Good morning, and thank you for having me. So I have to put basically two disclaimers in the beginning. First of all, I was somehow, my abstract suggests I give an overview over various kind of analog quantum computing topics, which I don't do. I decided to concentrate on one project only. The second is much more serious because, of course, speaking after Scott, only talks count that fit in your middle of the Venn diagram, and mine definitely does not. So, but well, you tell me afterwards. What, however, we are trying to do is to have actually usefulness as part of the goal, which is not in your Venn diagram. Oh, yes. Okay. So this is based on this paper, which is on the archive since a couple of months. And I want to start with all the courses on that. And in particular, I want to highlight the two people who kind of guarantee our usefulness, which is Anna and Martin, who are actually quantum chemists. So this whole project was developed with them. And then, of course, in particular, Nishat and Stefan, who really were doing all of the work. Okay, so quantum chemistry means we solve an electronic structure problem for a configuration of electrons and nuclei. And that typically means we have to have a Hamiltonian with the full Coulomb interactions, which is obviously hard in general. That's why the quantum chemists are at it already since a long time. But the question is, do we really need a quantum computer to solve this? And if we see these days quantum molecules kind of calculated with a quantum computer, these are typically kind of, so yesterday we saw something, some kind of strontium, I don't even know how this is called, but in Ashley's talk. They are great benchmarking, but they can definitely, I mean, when we first approached the quantum chemists with, oh yeah, we want to do quantum chemistry on a quantum computer, they were laughing at us. And I'm sure that many of you had similar reactions. So the question is, where can one actually potentially get some advantage from a quantum computer? And the most, not the only, but the most obvious answer is if we have strong correlations. And so that's where we basically do this. Just for comparison, here is this nice paper with, from Microsoft, which kind of gives a somewhat state-of-the-art estimate of the most important potential useful quantum computation problem, and where they fall in terms of how many raw qubits one needs, and what would be the runtime to solve one problem. And what we can see here, so these different things are for different errors and for different kind of gate times. So the gate times are between microseconds and nanoseconds. And these, as I say, are raw qubits. And as you can see, quantum chemistry doesn't fare that well. So it needs a couple of million of physical qubits. Well, we might be able to get there. But then if you have them and if error correction and everything like that is taken care of, then we have to kind of expect for a runtime between months and centuries. That is obviously not so good. So let's not go this route, but let's try to do useful things anyway. So the first thing is, where does the overhead actually come from? The first really hard problem is to map the target problem onto the quantum hardware. The The second is that these calculations are assume that you do quantum phase estimation, which is expensive. And the third is, of course, that you have a large overhead due to error correction. So what we try to kind of take some of the problems, make quantum dynamics out of it, and put that on the near-term hardware. And the rest of the talk is showing you how we do that. So first of all, we really want to leverage everything which the quantum chemists have done already, which is a lot. Second, we want, of course, to use state-of-the-art quantum hardware, which is, for example, Rydberg atom arrays, of which you, I think, have heard and will hear. And third, we want to do hardware efficient. So none of what we do is agnostic. It can be adjusted to other hardwares, but you have to do it. It doesn't run automatically on other hardware. So again, where do we need a quantum computer for if we have a strong correlation? So in principle, we have 3 elements in that. Obviously, we have high performance computing, which also the quantum chemists use. And then this is very special for quantum chemistry. They basically typically don't do their complicated chemistry all at once. They kind of bunch it, cluster it, simplify it, coarse grain it, etc., and make so-called model hamiltonians. And we basically take the model hamiltonians that the chemists already have made and use those. And what is, for example, a hard problem for them? Well, I talked about that in a second. So the third element is obviously quantum computer. And this is the only new element that we can add to that. We will introduce efficient multi-qubit gates and a high degree of programmability, and as I said, simulated time dynamics. And then we use all 3 of them together. So the type of problems for which we need strong correlations is, or a really good problem for that is if we have spin interactions with spins that are larger than 1/2. So, and for that, we can have any spin Hamiltonian, and we are not limiting ourselves to 1 and 2 spin interaction. In principle, we could go to 3, 4, whatever. So we are kind of having, I'm sorry, this is so small. So one good example of such a problem is the following molecule. This is a molecule that has a couple of high spins, and it is difficult to solve, but easy to obtain the model Hamiltonian, and it has a relatively natural mapping to the quantum hardware. And this is basically where we take this from. So this particular molecule is a catalyst, which is important for the oxygen evolving complex in photosynthesis. Yeah.
All electrons have spin ahead.
Yes.
And in chemistry,
yes,
we have.
That's exactly what this slide is about.
Okay, help me. Yeah.
So here in particular, what we have, typically this is true. So what we have here are in particular 4 manganese manganese atoms. This manganese is a transition metal which has 7 valence electrons, and then it has different types of so-called oxidation numbers, and these are either 3 or 4, as you can see here. These oxidation tells you how many of these valence electrons are actually used up for the chemical bonds that we have here. So that means if for this oxidation state 4 of them are used up. For oxidation state 3 of them are used up. And so the remaining 3 or 4 actually effectively act like a spin 3/2. And so what we have in this particular case is we have 3 spin 3/2 and 1 spin 2. And this is actually, if they would all kind of ferromagnetically interact, then this would be easy. We would just say, okay, let's just assume they are all parallel, and that's that. But it turns out there are 3 interactions, Coulomb interaction, which is actually, we don't even take into account, that localizes the electrons, and the quantum chemists have done this already. And then between the spins, there is exchange interaction, which is ferromagnetic, and super exchange interaction, which is anti-ferromagnetic. And in the end, we get a mix of that. And so even though we have only 4 of these large spins, this already gives a relatively non-trivial space. And so what the computational chemists do, they build a so-called model Hamiltonian that might look something like that, and gives this basically interaction between each one of them and each other. Here, ferromagnetic and anti-ferromagnetic. And in general, this gives just these high spins give a Hilbert space scaling of 2s plus 1 to the n, where n is the number of those spins and s is the spin. And please do note that this scaling is just multiplies whatever kind of other problems the quantum chemists have to solve here. So this is even for this very simple problem with the 4 big spins is basically 2 orders of magnitude more complicated total kind of Hilbert space for the quantum chemist. So that means now if we just limit our problem to high spins, that means we have to solve 3 problems. First, we have to represent the high spins. Second, we have to make sure that they interact all-to-all controlledly. And finally, and this is also very non-trivial, is we have to be able to read out chemically relevant quantity. And let me already tell you here that kind of going back to the quantum chemists and said, okay, we can now find the ground state is not good enough. They care about much more than that. And I will kind of now spend the rest of the talk with kind of giving you an overview over these 3 problems and how we solve them. So here are the 3 problems again. So we need the high spin, we need the non-local connectivity, and we need to have a good solution readout. And I will start with the non-local connectivity because that's a problem that basically has been solved already before we even started this. And this is the fact that in these Rydberg arrays, one can move the atoms around. And I'm going into very, very small detail about that because I think during this workshop, there have been and are others who talk about that. Misha, for example, later this afternoon. So the idea is we have this array and one can sort this and one can actually move all the atoms around. They have very good 2-qubit gates, 1-qubit and 2-qubit gates, and they are based on the so-called Rydberg blockade. Just as a brief reminder, this is based on the fact that Rydberg atoms interact very strongly with each other. So if they are far apart, we can excite a single Rydberg, 2 Rydberg, 3 Rydberg, etc. If we have a couple of atoms, if we have them close together, we can only excite 1 atom in a neighborhood into the Rydberg state, and all others are moved out of resonance by the Rydberg interaction. And this is a nonlinear gate, and this is the basis of all of the gates that we do. This is also, this is robust because it doesn't matter exactly how close they are together, they just have to be close enough together. Here is a movie that, I don't know, you will perhaps see again, just for how you can move these atoms around. What we need is actually a little different, and I will show that as a cartoon later. We need high fidelity gates, and we have a mixture of analog and digital control. So at the end, this gives us a high degree of programmability. The interactions can be manipulated just by the geometry. Our pulses are fully global, so we cannot, with the pulses, address single atoms. So it's very controllable, but not unlimited. So with that, the non-local connectivity is already done because we can always move the atoms close enough together that we need to interact. So how do we do the high spin? There have been quite a couple of good ideas about that, and we have tried a couple of these ideas out. But it turns out that the easiest way to do that is to just say, okay, if we need a spin S, we just take 2s spin half states, and that means 2s qubits. Very simple. Here is a cartoon of that. This is would be a spin 3 half state. And in order to make that kind of interact non-linearly, they have to be within one Rydberg radius. This is this circle that is given here. And the first thing I should say, so here is the control that we have. The qubit is encoded into some ground states, which can be where we have a driving field between them. And the Rydberg state couples only to the 1, but not to the 0. And that also can be independently driven. But both of these pulses are global for the whole system. So this encoding is very simple, but it has one problem, because not every state of 2s qubits is also an s spin state. So in order to have this spin state, we have to always project back into the fully symmetric state. So that means that for our interactions, we need several important 2s qubit gates. In principle, we need any, but in particular, 2 are important. The one is we need all-to-all interactions, which we just take here to be any kind of Heisenberg. And the second is the projection into the symmetric subspace. And the way how we do that for simplicity is we just do that with optimized pulses. And the nice thing, just a second, the nice thing about this pulses is that we can basically do that for for example, 1 pulse for every cluster of 3 qubits in this whole. Yes.
Chemistry, is it in terms of the fermionic operator, or you completely only
It spins. Right now it's just spins, yes. But we are not kind of limiting ourselves to any particular spin model. It can be single spin, 2 spin, 3 spin, and doesn't have to be symmetric, which is actually in quantum chemistry, it typically isn't. Yep.
So in the context of quantum chemistry problem, does spin dynamics actually affect the chemical properties?
Yes. It does.
But why are we fixing the fermionic like algebra? Like what it makes us do?
Because we haven't solved it all yet. So that's just the starting point.
Okay.
So we will get there. This is actually right now in the program we are working on that, but we haven't solved this yet. Okay.
It does include fluctuations, like this approach can include perturbative theory, for example. Basically.
Yeah, but this is I'm not going to show this yet today. So yeah.
But I'm still a little confused. If you have 3 electrons in the molecule, in the valence state, and you want to spin 3 halves, you're using 3 Rydberg atoms for it, right?
Yes,
so
exactly.
Why are you bothering? I mean, why don't you just connect those 3 Rydberg atoms as individual electrons? You're already using 3 for 3.
Because they first of all they do interact with each other, so we somehow have to map them to our Hamiltonian. But the second thing is that we do need they exist in nature only in this actual symmetric spin state. So as I said, not all states of 3 qubits are valid 3 half qubit states. Sorry, 3 half spin states. So, these 2 operations, they are just examples, but they are kind of important, as you will see in a second. And we use them using optimized pulses on both of those fields, and we are using GRAPE. And the pulses, they might, for example, look something like that. So this is really pure optimization. This is not that you can a priori say, oh, this is how they have to look like. And this is already this exists pretty long already. And there are a couple of projects of people who have used that in practice already. So this is already a well-proven method. And here I just want to kind of show, this is a little bit a similar picture as what Ashley showed yesterday morning. So here we compare these two gates, the Heisenberg and the projection gate. If we do the multi-qubit gate, and you can just look at only the lower one, because the difference between the upper and the lower is whether we optimize the two fields separately or together. And we compare that to two qubit operations. Both of them have a 10 to the minus 3 error. The reason we use that error is because that's what in the Rydberg array just right now is a fact. And the nice thing is that in this multi-qubit gate, it basically nearly does not depend on the number of qubits. Now, of course, we do that up to 8, okay? So in principle, of course, this is a very scant evidence. It doesn't prove anything. For our high spins, 8 is already pretty good, and it is enough. And 8 is also actually right now what the experimentalists can still well get into one Rydberg radius. So for now, this is good. This, of course, has to be higher eventually. And we compare that with just the 2 qubit gates, which basically grow, well, more or less exponentially for exactly the same gate and the same problem. So that is already a nice speed up, which kind of we got for free. We just tried that and turned out it actually works very well. So here is how we engineer the interaction. So here, of course, this set of spins is a little bit unrealistic and a little bit bigger. So here we have whatever spins we have, spin 2 spins we have, spin 1, etc. And we are now looking at a little bit simpler target Hamiltonian of only 2 qubit interactions. But in principle, we can, for example, include both Heisenberg and Dialoshenskii-Morea type interactions, which is a little bit more general than what the typical kind of condensed matter Hamiltonian. And the way this works is that we start with these things in the clusters, in their kind of spin S clusters. Then we move all of them that are supposed to interact with each other in pairs, run exactly that Hamiltonian pulse for the pairs, which kind of mediates long-range connectivity, because we can move them around as much as we want. But of course, this large spin encoding is violated, because we do that now for the qubits rather than for our spin S. So that means we have to go reconfigure it back into the original cluster and basically do the projection on the spin S states in order to work. And then we kind of combine these two and mix the inter and the intra-cluster states in a Floquet type manner. The nice thing is that one of these two angles actually doesn't have to be small. So this makes the whole thing a bit more efficient. And this realizes the target Hamiltonian on average. The nice thing about the Floquet engineering, as usual, is that higher errors can be either canceled out, or if we want higher terms, we actually can also explicitly take them into account this way. And we have a couple of examples of that, but I'm not going to show this. If you want to see it, I can show you later. Here is another kind of proof of the potential performance. So here we are looking at various more kind of condensed matter type project. Here is a spin 1/2 Heisenberg for a Kagome lattice, where we compare normal 2 qubit gates with kind of gates where we take this kind of triangular interaction already as a 3 qubit gate. In which case, and here the comparison is just how many gates can we get in the coherence time. The reason is why we take this kind of somewhat funny counting is that otherwise we get different quantities for the 2 qubit and the multi-qubit. And as you see, I mean, here the improvement that we get is, well, about a factor of 2. It's nice, but nothing to write home about. Similar, here we have just 2 particle Heisenberg, but for spin 5/2. Sorry, this is not just Heisenberg. This is a mixed Heisenberg, the Dialoshenskii-Morea. And again, we compare the 2 and the multi, and here, well, we get nearly no improvement. And then we look at the spin 2, a square lattice of spin 2 particles in 2 different modes, or for 2 different Hamiltonians. The first is a quadratic and biquadratic Hamiltonians, for which, and here please to note here, we have actually exponential scale here. We get about 1 order of magnitude, and if we go in addition with two very much higher orders here, we see that we gain quite a lot more from this case. So here we get about 2 orders of magnitude. At some point, we run out of computation time. We cannot actually try this higher. But it looks pretty promising also for other than pure chemistry problems. So that means this hardware optimized multi-qubit operations is efficient, and this Fouquet Hamiltonian can combine operations also very nicely. Okay. So now let's get to the readout. And this is something which I think in general has been always a little bit of a stepchild of this whole field. So we pretty much kind of started a little bit from zero. So what we do, we leverage the ability for efficient time evolution of the Rydberg simulator. Well, obviously that's what all this quantum computing is about. But also the ability in these kind of setups to perform so-called snapshot measurements. So what does that mean? We have this atom array, and every measurement is one picture of all of the atoms in the computational basis. So that means with one shot, we get whatever, if there are 256 atoms in the array, we get 256 kind of ones and zeros. And so we let our system evolve for different times and collect all of these sets. This is obviously an enormous amount of data, and we are trying to use as much of that as possible. And in order to do that, we have introduced a new quantity which we call operator with self-density of states. This depends on one operator A, which could be, which could be, for example, the unit operator. And if that's the unit operator, you will see that what this quantity D is basically just a spectrum of the system. But we can also use others, which then are resolved by the physical quantities, for example. I will show a little bit more about that. And here is basically the peaks that we would get in the spectrum. So why is this a good quantity, and how do we get it? So the thing is, here we really need to heavily kind of get our toolbox of both classical and quantum. And the thing is, one can show that this quantity can be found as an average over various evolution times, over all of these state samples, and over various observables. And this gives us 2 correlation functions. And I don't show you that this gets complicated unless you want to. The one comes from a time evolution of a known reference state, which therefore can be done efficiently classically. So no quantum computer needs for that. The second one is the time evolution of an unknown superposition state. And for that, we need the quantum computer. And for that, we run exactly this kind of time evolution that I showed you before with this rearranging, etc. And what we get is kind of shown here in more detail. I'm not going into that. The nice thing is that if we have one set of samples, we can find this dA, this operator with self-density of states for any kind of operator A that we want. And I show you an example why this is useful. So here is the very simple circuit diagram for what we do. We prepare a known reference state with S, then we do a control perturbation of various kinds, and ideally we try to kind of sample well with that, and then we run the time evolution on this, and then we can measure in parallel all of these atoms, which gives us, because we are in a measurement basis, 2 to the n observables. And yeah. So let me just go back briefly. So here we do this sampling. This is basically the hours. So choosing various hours. And that's actually a very good question. So these various hours, in principle, would sample fully. However, and this you will see in a second, we don't actually want fully. We want to because the chemists, they are more interested in the kind of low energy kind of part of the spectrum. So we will sample the low energy part kind of considerably heavier than the high energy part, if we know how to do that. It's not always clear. So the thing is, what we need to sample such that we get states that have a high overlap with whatever part of the spectrum at the end we want to see. You look, so
Where's
that A is not, the A is only in the classical post-processing. So here, this is the quantum circuits. The A comes in only classically. So we have two operations also, or two basic unitaries. The one is this disturbance or sampler. The other one is what we use for the observing, which is A. And for both of them, one can actually kind of choose what things one want to. That we get the superposition of the original state space and the disturbed one, because we start with the superposition state here. And then at the end, we look at the correlation between the original state and the disturbed one. And so one of the things that we, for example, get here for the simple example of just a simple Heisenberg of two spins, but these are spins we have. I mean, that's obviously a trivial problem. We can solve this, and we have solved this. This is, we can do, for example, direct diagonalization, and we get kind of 4 eigenvalues, and you see them by this gray lines here. And if we choose this A to be just the unit vector, then we get just the spectrum, and the spectrum is this black broken line here. This is basically what one would see if one would kind of measure this a molecule of that type experimentally. In our case, the broadening comes from the errors in the quantum computer. And we see immediately that there's a little bit of a problem, because this spectrum has only 3 lines, but we know there are 4. And in particular, we wanted low energy, and in particular, the lowest energy one is actually swallowed up here, because it just doesn't have that much weight. So what do? We change A to take into account only the total spin equals 3 sector, the total spin equals 2 sector, etc. All of these can be done with the same set of samples. And here you see that we actually get also this lowest line very nicely in this total S equals 0 sector. And we also see that the others are actually kind of fit much better the actual state here. So this is one way how one can actually resolve a spectrum better. Another thing that we can do is to, for example, get the susceptibility as a function of temperature. In this case, what we do, we take the sigma z, which gives us magnetization as for this operator A, and put the whole solution into a Boltzmann distribution, and this gives this curve here. Just to give you an idea how difficult this is. So this if we get the error bar to give this blue shaded region, we need 10K samples. If we want to do better, we get this purple one with 50K samples, and we haven't tried larger, but the black one is the exact solution. As I say, this is still a simple problem, can be calculated perfectly well. So, but now we go back to our somewhat more complicated molecule. And in this case, if we do the same thing and we just use A equals unity, we get the full spectrum. And here, this is not the full spectrum. This goes actually on in this direction here quite a bit. And again, the lines can be found. So this is still, I should be honest, this is still a problem that can be done with direct diagonalization. It takes already long, and we cannot really get bigger, but so far we can still compare to perfect calculation. And so, as you can see, well, we can somehow reproduce the spectrum with the quantum computer. But then what we do, we actually now try to zoom in this lower energy kind of region, because that's what kind of at the end kind of, for example, in chemistry dominates chemical reactions and so on. And we do exactly the same thing that I did before, namely we kind of look into these various kind of spin sectors here and resolve the spin a lot better. And the first thing that gives us is that we get a lot higher resolution of the spectrum, and actually kind of indeed we see all of these lines that the direct diagonalization gives us, but it gives us more than that. Right? A direct diagonalization, unless we can really have enough calculational power to also exactly calculate all the eigenvectors, we don't know what these lines actually mean. Where do they come from? And what we can do with this choosing this particular projection into a particular state, it tells us where these lines come from physically. And in particular, there was a long-standing open question about this is the same molecule as here, about two possible configurations of this. And this is, I think you cannot see that, they are called S2H1b and S2H2b, where it's not so clear whether this low energy kind of distribution comes has the 5½ above the 7½ and then the 9½ etc., or whether the other configuration has that. That's you can measure the spectrum experimentally, but you cannot experimentally exactly say from which configuration that comes. And we can now say, okay, we run this configuration through our process and this configuration through the process. We compare with the experiment, and we see that obviously this first configuration is the one that is the more likely one in reality. So these are somehow some of the things that we can do. Sorry, this one I said already. We have a couple of newer results where we go a little bit further. These are really very new and not published yet, and also not kind of cleaned up yet, etc. We do go back to the very simple kind of Hamiltonian and just do this kind of, spaghetti diagrams that the chemists typically do, and look at what are and here this is just the energy over the bond length of H2. And here our starting state is the Hartree-Fock state, which is very simple to calculate classically. And then this overlap is actually very easy. And these calculations here, they are relatively simple to do. Then we do the same thing for lithium hydride and also start with the Hartree-Fock. And here we already get a spectrum that looks like this, just from kind of running this whole this whole process. And this one is already kind of starting to get high. Okay, now let me just finish up. As I already hinted before, this is of course not really limited to quantum chemistry. This can also be used for condensed matter, for example, 2D magnetic Hamiltonian. And with that, we can do band structures, and Methods are similar, but here, for example, and that goes a little bit back to Lynn's question before, here we sample not over all possible perturbation operators are, but only over those, over the different kind of poly X strings, because they are the one they give us at the end the magnetism here. So we can basically choose what kind of information do we want, and then we can choose what information do we then classically want to distill out of that by choosing the operator A. And here this is all kind of mixed together, so I'm not going into much detail here. So what is next? So the first thing is this operator resolved density of states is as I say, that it was kind of really new for this paper. There's a lot more that one can take out. Try a lot of different operators A. So far we also try out only diagonal. NAN. The next step is also to go to actually off-diagonal quantities. So we are just right now trying this out. There are no results about that yet. Then the next big question is error correction. I mean, as Misha will tell you later, there's very good error correction on their machine for logical qubits. These are not logical qubits. How do we do error correction for something like this? This is a little bit a red herring, because the dynamics of chemical reactions, that quantum chemists can do that actually pretty well once they know the low-level spectrum. So we don't need to do anything. We could also say, okay, we do the dynamics by just running another Hamiltonian that simulates kind of the dynamics of the chemistry. But in principle, right now, that is not needed. And then, of course, the biggie is to actually go to fermions. This is the question that Susanne asked before. Okay, where we really go into from pure spin to the full fermions, where the electrons also can move around. And that's it. So this is basically the full program again. And with that, I want to thank you.
Yep. So for green functions, do you first use the OTOP-like circuit and measure the time correlation and then do a Fourier transform?
So what we do here, and so what we do here, and I need to read this out because I never can remember that. So what we do, as I say, we disturb only in this X operators. And what we get is the single particle Green's function, which is basically the X of somewhere of one of these surroundings. So what we do, we start with a starting state where we kind of flip one spin in the middle, and then we let it evolve, and then we compare. We have the Green's function between this X operator at in the middle, and any kind of X operator at a finite time here, and that is exactly the Green's function that is shown here. Or well, this is the Fourier transform.
Do a Fourier transform.
Yeah, exactly.
And you start from the ground state.
And here we start from the ground state, and then take as this reference state this single spin flipped.
So because it's a particularly simple problem, you can forget the ground.
Yes, exactly. Yes.
So
So the point is, it's always good to have some kind of good reference state, which up to a point already mimics what the problem is doing. So here, this is the ground state, because we know that the ground state for a simple ferromagnetic Heisenberg is all down, right? In the case of the molecules, Hartwig fork, which basically can be done for pretty much any size molecule, not any size, but very high up, is a very good starting state, because that means that if we start from there, the overlap that we get at the end is already non-zero for a lot of our sample space. So this kind of reference state finding is actually a priori somewhat non-trivial, and for the problems that I have shown you, it's kind of pretty straightforward, but it's not necessarily straightforward for every single possible. Yeah.
Yeah, very beautiful results. So I have a question about the error correction part. So I think imagine that by using this symmetric subspace of the spin example, you're already doing some sort of encoding that actually encodes a sort of logical qubit into this.
Yes, yes, yes,
So have you
exactly.
thought about the possibility of doing error correction or at least error detection, maybe with minimal actual overhead?
Yes.
By already using
Yes.
this natural.
We actually are thinking about that, yes, but we have no results yet. So, but yes, that's a very good point.
Unfortunately, not so simple.
It's not simple, yeah, but I mean,
Yeah,
this-
yeah, I agree. Well,
no, I mean, but the question is a bad error. I mean, it's a bad error correction code for anything that you want to do with the typical kind of 2-qubit gates, etc. But for this one, we need to come up with something like that, obviously, right? But yes, I mean, this is.
But I imagine that could be at least a simple error detecting code. Right? For instance, I can imagine that the Rydberg decay might just get you out of the symmetric subspace.
Yeah.
And if you push that down those events, then you could potentially already get better results. That could be a simple.
Yes, I don't know how well that scales, etc. But yes.
Leakage, yes, leakage you can.
Yeah, exactly.
But it's not scale well.
That's
Yes.
So my question's about the part of mapping the chemistry systems to
Yeah.
spin systems. So I'm wondering, firstly, is this somehow, let's say, a popular approach in the sort of classic, quantum chemistry community? And also,
Yes, and it kind of popular. I mean, it depends a little bit on where you go to, but this kind of building of model Hamiltonians is basically what. Now I don't find it anymore as it happens. This building of model Hamiltonians is basically the bread and butter of people like Martin Heidgordon. And this is actually by itself already a kind of a pretty non-trivial thing. But as I say, they know a lot better how to do that because they know the chemistry a lot better. But yes.
Is it sort of considered that these methods can deliver chemical accuracy in the end?
Yes. And I mean, the accuracy that we get here in the spin sector is actually already very good. And I right now I don't have exact numbers how this, because as I say, what we compare with is the direct Hamiltonian and not really the best kind of measurements.
It of course depends on system. For some other systems, it will just not be.
It depends on system, depends on how good the quantum computer is, right? If the quantum computer has a smaller error, our lines get narrower, etc., right? So it depends, but yes, we are definitely shooting for accuracy with that.
May I just make a comment that at least for the case for the fermionic mapping to the higher level, we have a recent work to generalize the fermionic mapping to the spin tree. Of course, we haven't done it for chemistry, but for a hollow model of tree.
Okay, thank you. I'll have a look.